Okay, today we're happy to have Sebastian tell me about open Gromov-Witten invariants.
Okay. Yeah, so thank you for the invitation. Right, so yes, kind of the point of, okay, so the point of this talk is going to be explaining how to, right, like a way of defining the open Gromov-Witten invariance in characteristic 0. So I will just start by explaining what we're trying to do in detail. So in this talk, I'm going to let M omega denote a closed symplectic manifold, and L is going to denote a closed Lagrangian submanifold. Okay, right, and so right by open, right, so I guess Gromov-Witten invariants are supposed to be counts of like pseudoholomorphic curves in a symplectic manifold. So what we mean by open Gromov-Witten invariance is that we are right, we're trying to count disks with or curves with boundary on a Lagrangian. So right, we say that the gen is 0. Open Gromov-Witten invariance. Should count J holomorphic disks in M with boundary on F. Okay. So right, so we do something like that, and then maybe for ease of exposition, I'll just assume for right now that you know, M is, say, a Calabi-Yau threefold. Calabi-Yau threefold. And L is also of 0. Right, then what you can say is that right, the moduli space, right, the moduli spaces of such disks where with M-1 here means that we're looking at disks with no interior marked points and no boundary marked points, has right virtual dimension 0. Okay. Right. So in principle, in this case, you could just count right, all such disks. So I mean, you know, if we kind of assume we have some like framework for virtual perturbations or whatever, right, which I won't really address in this talk, right, we can set right, this thing that I'll call M-1J to be equal to this count, and you right, so you should kind of right, so you should expect this to be a rational number because you know, we're just trying to count, you know, we're just trying to define some enumerative quantity here, and then you should maybe allow yourself to divide by positive integers to account for multiple covers of disks or something. Right, and so the problem with looking at this quantity directly is that if you literally try to take the count of disks with boundary on a Lagrangian, then you're going to get something that is not independent of this almost complex structure. Okay, so right, this quantity is going to depend on J, and the reason for that is that, you know, okay, so maybe I'll just say that moduli spaces of pseudoholomorphic disks have yeah, I guess I'll right. So I guess maybe I will just explain why this is an issue. So, I guess like kind of an analogy with the case for closed Gromov-Witten invariants, what I would like to do to show that the quantity like this is an invariant is to consider some like generic path of almost complex structures, like I guess like connecting to like omega tame or omega compatible ones, and then I would just like to exhibit these two moduli spaces as the boundary of another of like some other like manifold or Konishi space that I get by counting like solutions to some time-dependent version of the J-holomorphic curve equation. And if I do that, the issue with having boundary here is that you're going to see configurations which don't look like disks at the endpoints that can kind of spoil the invariance of the count. So, in particular, what can happen is that so if I have a disk with no homologous boundary or something, then the boundary can just kind of collapse to a point. So I can think of this as like a smooth, like closed holomorphic sphere with which like intersects my Lagrangian transversely somewhere, or not transversely, but just intersects it. Or it can break up into some kind of nodal configuration. Okay. And so if you want to try and count disks with the Lagrangian boundary in any kind of meaningful sense, you need to do something to kind of correct for, I guess, these two types of boundary bubbling. So I guess at first this probably looks scarier, but I guess like it kind of turns out to not be so bad. So to deal with this kind of sphere bobbling, what you should do is you should assume that your Lagrangian is null homologous. Right. Sorry, this is page 10. And equip it with the bounding chain, which I guess I'll just say lives in relative homology. So, so like somehow what you should do is you should consider the space of holomorphic spheres which intersect this chain, and then you should add it to, then you should like add it to this count. And so what ends up happening is that like the count of such spheres is going to transform the same way as, I guess like this, or I guess like it'll like, it's like, so sorry. So the count, so the count of spheres which intersect this 4-chain is going to fail to be invariant under changes of almost complex structure. But like, I guess like the kinds of sphere bubbles that you'll see as you vary in a path of almost complex structures will turn out to kind of cancel with the sphere bubbles that you see here. So, so this deals with this type of bubbling. But dealing with disk bubbling actually takes a little bit more effort, and introduces some new technical complications, which I will kind of try to talk about. Okay, so to deal with the second type of issue, there's an idea which goes back to originally Joyce, and then kind of implemented by Fukaya and Solomon Tukachinsky. So, so maybe I'll just say now, Fukaya did this for Maslov zero Lagrangians in Calabi-Yau threefolds, and it was extended to arbitrary dimensions. But under some regularity hypotheses. By Solomon and Tukachinsky. And the thing you should do is that you should equip L with a bounding cochain. So L with cochain in the sense of Fukaya A-infinity. So I think I'll just right. So I guess I'll spend like the next little while talking about what this is, and then try to come back to the problem of defining open Gromov-Witten invariants. And this is, I guess, going to require us to sort of explain how Lagrangian homology works. So I want to let K the field, which I'm just going to take to be of characteristic 0 in this talk. And then for such a, and then, given a field like this, I'm going to define the Novikov ring. Novikov ring under K. And the elements of this thing consist of formal sums, which look like this. So T is just going to be some formal variable. The coefficients here land inside K. So we're going to assume the exponents are non-negative and that they kind of go off to infinity. So not sure if people wouldn't have seen it before, but the idea here is that you're kind of using these lambda i's to record the areas of holomorphic disks. So when I wrote down this moduli, I guess like when I wrote down this moduli space, I didn't give you like a constraint on the homology class that these holomorphic disks should live in. So so I guess the moduli spaces you look at aren't actually going to be compact. They're only going to have some proper map to the real numbers, but working with this infinite series ring sort of lets us avoid convergence issues of this sort. And I'll just say later that this has a evaluation which maps a sum of this form to the first, or to the exponent of the first non-zero coefficient. So, Okay. So this is the so I guess these are the coefficients that we're going to be working with. And so I want to do so I want to do something which maybe now looks a little bit unnecessarily abstract, which I apologize. And I want to let C star of lambda K denote a chain level model for the ordinary cohomology of L with Novikov coefficients. So, so in practice, you should think of this as either the de Rham complex or the Morse, the space of Morse cochains associated to some more small function on F. So the distinction between these things will be important later, which is why I'm not committing to a specific chain level model yet. Okay, so so associated to a Lagrangian, we will have a Fukaya A-infinity algebra, which consists of operations M sub k k copies of C star of L with grading shifted down by 1 to C star of L. Okay, and then these should satisfy the what are called the curved infinity relations. Okay, which I will just write like this. Okay, so so saying that if you take like any like any k tuple of k tuple of chains, and I look at the sum over over all like ways of composing like k array operations, then then this should vanish. And I guess for the record, this is going to be some kind of proposal sign. So, right. Okay. You know. Right. So I can imagine. So I would guess that it's maybe safe to assume that like most people here will have thought about like the Fukaya category and the usual like the usual A-infinity relation before. Maybe in some kind of like exact or monotone setting. But I guess what's sort of relevant here is that we are working in a situation where we're interested in Lagrangians, which kind of bound some interesting configurations of holomorphic disks. And so this can actually cause like the usual A-infinity relations to to like fail in some sense. So should just be clear that here I'm letting k be greater than or equal to 0. So if you write out these relations for so for k equal to 1, then ignoring signs, they are going to look something like this. So I'll have like I guess the composition of M1 with itself, but this is actually going to fail to be a differential because you are going to have some additional terms, which involve this M0 thing. So so in terms of looking at the moduli like moduli spaces of disks with two boundary marked points, you kind of read off this equation by looking at you read off this equation by looking at the codimension 1 boundary strata of such things. So I guess the term that you're expecting to see should sort of look something like this. So it's kind of like a form of strip breaking. And the other thing that can happen is that you can take a holomorphic disk with two mark points, and then you can just see something like this, or some disk bubble just kind of appear on the side of this thing. Okay, so you want to think of M0 as an algebraic amount of disk bubbles. Right. So, right. And so like historically, right, like I guess, or, you know, people kind of didn't expect to see, you know, right, terms like this in the Fukaya A-infinity algebra. So, I mean, right. So like one reason to think that this is unexpected is, I guess, by the homological mirror symmetry conjecture. So, you know, if you work in the setting of a Calabi-Yau threefold, you would kind of expect the Fukaya category of such a thing to be like quasi-equivalent somehow to a, right, to like a DG category. So you can think of like the, right, some version of the category of coherent sheaves on another space. And right, so this thing is, right, so this thing is, you know, I guess like, you know, is just kind of a category where all the Hom sets have honest differentials. So you would never see something like this there. So that kind of tells you that there should be some way of sort of algebraically, right, removing these curvature terms. And so I guess this led, I guess, Kontsevich and then Fukaya to Ono to formulate the notion of a bounding cochain. So we say that, I guess, some B in, I guess I'll say C1 of L is a bounding cochain. Right, if, well, okay, so first we should say it has positive valuation, but then the interesting constraint is that it should satisfy this condition. So right, so if I look at like all possible compositions of B with itself of an arbitrarily high order, then the sum of all such things should vanish. Okay. Right. So yeah, so I guess maybe I will just quickly say, right, that the reason this is one reason this is helpful is that if I, right, is that if I'm given a bounding cochain, I can define deformed A-infinity operations by looking at right, some kind of sum right, so an infinite sum. Of deformed operators. I'll just okay. Right. So so what I kind of do is I just take the usual A-infinity operations and then I you know just like add you know arbitrarily many factors of B like in between each of the slots. Okay. And so if I do right, and so if B is a bounding cochain, right, then the set of right, then the operations defined this way are an unpermanent A-infinity algebra, right? Yeah, I guess because yeah, so so the infinite sum over here should be the definition of like M0 deformed by B in this setting, and that condition says that this thing vanishes. Okay, right. So we have this, and then in this context, there is a definition first due to Fukaya of the open Gromov-Witten invariants, right? So we say that, I guess the open potential, which I'll just say is some object associated to the pair L equipped with a bounding cochain, is defined to be this infinite sum. So I start by taking this naive count of disks that I had before, this n-1, and then I will add to it this quantity. So it's sum from 0 to infinity, of mk evaluated at b to the power k, paired with b. So right here, this just denotes the Poincare pairing. Okay. So geometrically, what we're doing, is we're taking this, so we're starting with this naive count of disks. So it's kind of what n-1 should be, and then we are adding to it some kind of count of disks with an which are allowed to have an arbitrary number of marked points, but we're saying these marked points sort of have incidence conditions which are determined by this bounding cochain. So I guess, so the reason for these factors of 1 over k plus 1 here is because the way that we've set up these A-infinity operations, they're supposed to count disks with, so I mean, you want to think of, I guess, this coefficient as a count of disks with k plus 1 boundary marked points, all of which have, all of which should sort of have an incidence condition given by b here. But in the definition of these A-infinity operations, one of these marked points is going to be distinguished as an output. So to account for that, we want to divide by 1 over k plus 1. Okay. And I guess like the first thing that you would want to ask about this open Gromov-Witten potential is, to what extent is it, does it depend on the choice of bounding cochain? So, so at the beginning of the talk, I said we should do this to kind of correct some failure of this quantity to be well defined, but then, we seem to have introduced some other choice that this depends on. So I'll just remark that, showing that this potential is independent in B, maybe up to what's called gauge equivalence, which, is a natural notion of equivalence for bounding cochains, which I'll tell you one way of thinking about in a second. Requires that the Poincare pairing have an additional symmetry. So it requires that this is cyclically symmetric. Okay, and so what I mean by that is that if I look at this operation with k plus 1 inputs, then I should be able to cyclically permute the inputs and get something which coincides with the original operation up to like a cosine sign or something. So yeah. So it should, right. So it should be able to, right. So we should be allowed to kind of cyclically permute these things. So, right, like, right. So I guess like at first glance, you would kind of expect that this should be obvious because what the cyclic permutation sort of corresponds to is just taking these incidence conditions on disks with mark points and then rotating them. So you would sort of expect this to follow from the S1 symmetry of a disk. Right. So the problem with, right, but the problem with doing that is that when you actually define these A-infinity operations, you have to say something to make sure that you get, right, that you achieve transversality for these moduli spaces. And so in practice, this is sort of going to involve doing some kind of domain-dependent perturbation, right? So like in particular, like, constructing a Kuranichi structure is, right, is a type of domain-dependent perturbation. And it's just kind of technically a difficult problem to, ensure that you get something which is cyclically symmetric here. And I guess the remote, right, like the thing to say is it's not known how to achieve cyclic symmetry unless we take as our chain level model, right, the wrong complex of M. Okay, and so in particular, this forces us to always be working over a field which contains the real numbers. And yeah. So I mean, maybe I'll just sort of explain something which goes wrong if we if we try to do this with or I guess like some issue that one would have to deal with if you were to try to do this with, say, smooth singular chains. So, right, so if we took, right, so star of L, right, to be smooth, right, so complex is smooth singular chains. Let's say it over the Novikov field with Q coefficients, then the way that you would like to define the A-infinity operations on this thing is by, taking some fiber product with chains of, so we want to define, let's say, right, this quantity, right, by taking a fiber product. Okay, so I'm just going to assume that like alpha 0 through alpha k are like singular chains. So I can take the product of k plus one of these chains. There's a map from this into the product of L with k plus one copies of itself. And I also want to consider like the moduli space of disks with k plus one boundary mark points. So this is right moduli space. This where here beta is just going to be some relative homology class, which I just kind of want to remember for this discussion. Okay. So if I want to, so like assuming that I've done something like chosen, fundamental chains on all of these moduli spaces consistently, if I want to take the fiber product of, right, if I want to take the fiber product of these two things and get another smooth singular chain, then I would need one of these two maps to be a subversion. Okay. So I guess for dimensional reasons, I could kind of, I could like sort of never even ask that that this map be a subversion. Right. But then it, there's kind of going to be a difficulty with trying to think about things in this way. And right, the issue comes from just noticing that the virtual dimension of nk plus 1 j beta is going to be something which looks like k minus 2 plus plus the Maslov class of beta. So like this is going to be some constant which just depends on just depends on this second homology class. And you can see that this quantity is actually so it grows like this in terms of k. But if I assume that the dimension of L is at least 2, which is kind of the first interesting case, then you see that the dimension of this thing is actually going to be growing faster than the dimension of this. Okay. And so and so the point that I want to make here is that if I'm in some situation where this moduli space is like actually a smooth manifold, then the evaluation map is never a submersion. Okay. And so it's not like essential, it's not completely essential to know about, but I guess it's interesting to know that you can never define sort of Lagrangian Floer theory using singular chains without using like some kind of Cartesian structures or whatever. So so if you use so even if you used sort of domain dependent perturbations and you somehow got enough transversality to show that all of these things were smooth manifolds of the correct dimension, you would still not have enough to define the A-infinity algebra this way. So in particular, if you want to do something without perturbations in order to try and maintain the cyclic symmetry that you see on the disk, you would just never be able to achieve cyclic symmetry. And so this is sort of kind of a hint that this sort of thing is the wrong, the wrong notion to use geometrically. Okay, so
before you utilize making, so you said that you have to use Durham complex.
Yes.
I mean, is it like you have to use Durham complex, or you can also use something like polynomial differential forms?
Yeah. So the reason that you want to be working with the Durham complex is because in that case you would only need one of these boundary evaluation maps to be a submersion. Right. So I can say that if I take the 0th marked point and I look at the evaluation map there, then if that's a submersion, I can push forward a differential form along this thing, and then that's then that's allowed. I think nobody has tried. I'm not sure what the issue is with trying to do this with rational differential forms though.
Because that's, I guess, defined over Q.
Right, that's defined over Q, but constructing smooth structures in LS spaces. Kind of a difficult thing, and then it's unclear what you would need. It's unclear what you would need to make this work for rational differential forms, and then it's certainly the kind of thing that Fukaya would have probably thought of, but I don't know off the top of my head if or what exactly goes wrong there. Okay. Right. So before I move on, I'm just going to say why why this condition is necessary for defining the open Gromov-Witten invariant. So if I take a path, it's a T, of bounding cochains, then, I guess the naive thing that I could do to try and show that I could get an invariant is to evaluate it this path and like, right, and like check that its derivative with respect to t vanishes. So, right, I guess if I, yes, still on the board. So if I try to write this out, I can see that m minus 1 does not depend, right, does not depend on t. So this is really just equal to, right, the derivative of this sum involving the high order terms. Evaluated at the b sub t. So I will just differentiate each of these terms using the product rule. So this is going to give me an expression that looks like this. Okay. So right. So this comes from differentiate. From differentiating in the first k inputs, and then I can also differentiate in the last input and get this. Okay. So from here, what I would like to do is to just use cyclic symmetry to move this term into the last slot. So this is going to be equal to the sum of, right, all compositions of BT paired with dBT dt, right? Where the factor of k plus 1 has now vanished because we have, right, because there are like k terms like this involving dB dt is one of the inputs. And then this last term is going to vanish because BT is the path of bounding cochains by the Maurer-Cartan equation. Okay, right. So this, right, so this is how cyclic symmetry is used here. And yeah, so yeah, so I guess, right, so, right, so I guess like, what I'm going to tell you about now is sort of a way of like thinking about this, using some kind of different chain level structure. Okay, I guess like kind of the observation here is that, right, cyclic symmetry of this pairing should imply that, such a thing is going to define an infinity bimodule homomorphism. Right, which I guess is also called an infinity inner product. In the literature, which is going to go from the diagonal bimodule to, right, the dual of A, where here A is just going to be C star of L. Okay, so this is, right, okay. So, I mean, right, so, right, so the A-infinity bimodule homomorphism that it defines here is literally just going to consist of a map of vector spaces in this setting. So I think, so I mean, right, so maybe the first thing to say about this is that, you can construct some kind of right, appropriate chain level generalization of this. So let's say under, right. So when I wrote about this, I did it under some regularity assumptions, which I'll talk about briefly in a second. But what you can say is that there is sort of a homotopy cyclic. A-infinity bimodule quasi-isomorphism which goes from the diagonal to the dual. And in this case, we're going to be thinking of A as the Morse cochain complex. L over the Novikov ring where the characteristic, right, where the characteristic of K is going to be equal to 0. Okay, so right, just to explain right what's happening here. So you know, so I guess like unlike the case with a cyclic pairing, phi is going to consist of now an infinite family of linear maps of the following form. It goes from p plus q plus 1 copies of A and has an output, right, and has an output in a dual. So I'll just remark that in the strictly cyclic case, we would have that phi of pq vanishes for, right, if one of these higher, right, one of these, right, if p is greater than 0 or q is equal, or q is greater than 0, so we really do only just have like one map of vector spaces there. And then since we're using the, right, like the Morse cochain complex, we are counting something slightly different. So yes, for a real chain level definition of this, you know, you can follow the work of Maurer-Cartan, and also Woodward, and some other people. And, you know, you can define A-infinity operations in the Morse complex. Right, which instead of counting disks are now going to have to count, right, what I'll call holomorphic Perley trees. So, so you should think that you can take a tree, and then you'll like replace the vertices of the tree with holomorphic disks with boundary on L, and the edges of the tree are going to get replaced with gradient flow lines of some fixed Morse function on L, or like a perturbation of it, which is like trivial near, right, which is trivial near the critical points or something. So, I mean, right, so I guess there are kind of two technical remarks about this. So on the one hand, this, right, doesn't require submersivity of evaluation maps. Which is kind of, right, which is, I guess, sort of the technical reason that it's difficult to construct cyclic pairings in the de Rham or the singular model. And the reason that we don't care about subversivity of evaluation maps is because, to make sense of this count of trees, we only need that, these moduli spaces of disks intersect the stable and unstable manifolds of these Morse flow lines transversely. So this condition is just going to tell you that the moduli spaces of Perley trees are going to be in virtual dimensions 0 and 1 are going to be cut out transversely, and that's enough for you to define these A-infinity operations. So it requires sort of less work analytically to define these things. But of course, the issue with using this for open Gromov-Witten theory is that if you do this, you get something which is sort of manifestly not cyclically symmetric, because now we've even if you get cyclic symmetry of perturbation data or whatever, there's just going to be broken, but cyclic symmetry is just going to be violated because each each of these gradient flow lines should be asymptotic to a critical point of a Morse function. And so this can just fail to be cyclically symmetric if you choose the wrong Morse function on F or on L. Okay.
Is there some general statement that you can make if the underlying chain complex is finite dimensional, then you cannot have cyclic symmetry? Or
No, there's not. I guess, yeah, I guess that's actually maybe a good thing to say as a piece of motivation. So I guess the way that we want to think about the bimodule, the bimodule homomorphism constructed in that theorem is as some sort of chain level upgrade of a result of Kontsevich-Stoigelman, which I'm not going to have time to fully explain, but what it says is that if I consider a let's just say let's just say a finite dimensional A-infinity algebra with de Rham complex in characteristic 0, then it has a minimal model, meaning one for which the differential vanishes. With a cyclic pairing. So in some sense, it's actually easier to get, So in some sense, it's actually easier to get cyclic structures on finite dimensional things because there's just sort of some kind of homological perturbation trick that you can use, and secretly, secretly, let me also just say. So this should also be what's called a strong proper, should have a strong proper Calabi-Yau structure, which is a condition that I'm not going to have time to explain. But secretly, the construction of this thing sort of, is sort of like a chain level version of this result. So, the way that you would prove this theorem is you kind of think about counting some Perley trees in a way that defines a non-degenerate class in the negative cyclic homology of L for you, and then from this at the chain level you can produce an A-infinity bimodule homomorphism which has this form, and then on homology is going to restrict to one of the things that Kontsevich and Soiberman constructed. Okay, so I think right. So I think at this point I will just kind of end things by by discussing open Gromov-Witten invariants again. So, given this, there is an open Gromov-Witten potential, which I'm going to call phi, which I'll call 5b, which is defined like the one that we had before. So, the only difference is that instead of just looking at the cyclic pairing, we're also going to incorporate higher order terms in this potential. So, and then this lives in again, line decay. So here, instead of looking at m-1, I'm going to look at a count of curly trees without exterior edges, which is just which is just sort of necessary in the Morse model. And then, as before, B is the bounding cochain. For the A-infinity algebra. Based on the Morse complex. And I will just kind of say for the record that gauge invariance of this thing, so independence of the bounding cochain, follows from an old result of Cho-Hun Cho and Symplectic. So they kind of I guess considered potentials of this form in an old paper about homotopy cyclic products, but I guess it was just unclear what the correct thing to count symplectically was. Okay, so so I guess we can kind of define this thing over arbitrary fields of characteristic 0. I think the last thing that I want to point out is that there's actually thinking about the field where these Gromov-Witten invariants live is sort of an interesting thing to do. So one cheap corollary that you get from this is that if you take L to be a rational homology sphere, then you can say that it has open Gromov-Witten invariants valued in the rational. So there is so there's some result in FO Cube's book which says that if you take any any rational homology sphere, you can restrict to a minimal model for its A-infinity algebra. You can show that 0 is a bounding cochain or such a thing. So bounding cochain always exists, but in particular, it's going to but in particular, it's going to be defined over the rational numbers just for homology reasons. So that tells you that by looking at the coefficients of this, by looking at the coefficients of this thing, you can extract open Gromov-Witten invariants, which are just rational numbers, which you would not be able to do in the draw model. But it's not the case that, that any Lagrangian is going to have rational open Gromov-Witten invariants. So another result which is kind of orthogonal to all of this is that here is immersed threefold. With open Gromov-Witten invariants that lie in an algebraic extension of Q. And so the failure, right? So the failure of these things to be rational sort of stems from the fact that you need to, right? That you need to equip Lagrangian with like some sort of like non-trivial piece of data in order to get, right? In order to get well-defined invariants. And so from that perspective, it's sort of interesting to think about like, you know, over which field, right? Like over which fields a Lagrangian is defined, and this is going to have, you know, something to say about like the enumerative, right? The enumerative invariants of this thing. But I guess I'm out of time now, so I'll stop. So thanks.
So what does it mean in that theorem under regularity assumptions?
Okay, so right, so I'm right. So what I'm doing is I'm just right assuming that right the moduli spaces, so all moduli spaces of curly trees of dimension, let's say a virtual dimension less than or equal to 1 are transversely cut out orbifolds. Right, of the expected dimension. So, right, so I guess like the two like main instances where these are satisfied are like, right. So like one example is like, you know, any Lagrangian submanifold, for which I guess Solomon and Tukachinsky define open Gromov-Witten invariants will satisfy this. They just kind of assume something. They assume that like all high-dimensional moduli spaces of disks are transversely cut out, which is something much stronger. But then the other case where this is satisfied is for any monotone Lagrangian. It was like following the work of Biron-Cornea, and I think that that level of generality is is kind of new. But the regularity assumptions here like aren't really essential. It's just something, right? It's just something that I wanted to do to make writing the paper easier. But if you had like kind of appropriate Kuraneshi structures on, let's say all, I guess like all curly trees of virtual dimension less than or equal to 1, where you should also be allowing the trees to have like interior marked points. We should also be allowing the disks on these curly trees to have interior marked points. Then, right, like then everything would work for this. So, did that answer? Okay. Yeah.
I mean, does the theorem involve like using some kind of minimal models? Like, why do you have to work over a field?
Why do I have to work over a field? Yeah, I guess. Yeah. So. Yeah, I think it might, yeah, I think it might not be essential. Like I'm always, yeah, like So like you definitely need characteristic 0 for like that, right? You need characteristic 0 for this part. I think if you strengthen this to assume that all of these moduli spaces were manifolds, then yeah, you could just do this in characters. Yeah, then you could do this construction in characteristic 0, but you know, maybe I would want to like think a little bit more before claiming that definitively.
And is it possible to draw what kind of counts PQ?
Yeah, sure. So okay, so right, so I guess right, we start by, you know, yeah, so I guess, you know, we're going to start by defining, I guess. Yeah, I'll just say it's like some phi in the dual space of cyclic chains on A. And so the kinds of things, right, the kinds of trees that we're going to count are things like this. So you can have an arbitrary number of boundary input, right, of boundary inputs, and then one output. And at this kind of central component where we have the output, we are going to count disks which have interior marked points constrained to lie on circles, which we kind of normalize to lie away from the boundary of these disks. Okay, so you should you should think of these marked points as kind of like as like quite literally as quite literally trivializing this like the S1 action given by rotating this disk. Okay, so by doing this and only counting things which have an output at like a top degree class in M, we're going to get something which lives in the dual space like this. So this is really right. So I guess like this count is really going to be something that we'll write as sum, just say phi sub M, right, where there's a formal variable of degree 2 because we're looking at cyclic chains. And then what we do is we just take is that we're going to map this thing. So we define a bimodular homomorphism by setting. We're using a formula like this. So I'll say that I should use different letters for this. So this is going to be called phi tilde now. This is phi tilde of, let's just say, plus or minus 1 cyclic permutation here. So so something like this. To answer your question, like these are the disks that you count with some algebraic procedure for extracting a bimodular homomorphism from this, and then it's like this specific thing on the chain level because you want something which is homotopy cyclic, whatever that means.